A few months ago, when we first talked about acid-base reactions, we saw how acid rain could melt the face off a statue, which is better than melting your face off, which some acids can do, so consider yourself lucky. Acid rain forms when sulfur dioxide emitted from burning fossil fuels reacts with water in the air to form sulfuric acid. And back when acid rain was at its worst in the 80s and 90s, it was the scourge of pristine waterways all over Europe and North America. Some rivers and streams were left completely devoid of algae and fish. In Montana, where I live, we saw quite a bit of acid rain too, as that statue could attest, but oddly enough, rivers and streams here did not suffer the same horrible effects as other places. This that I'm standing in right now is the Clark Fork River. It remains relatively unharmed by acid rain. In fact, when the water that fed it had a pH of 4.5, the river remained basic. This is a dropper full of dilute sulfuric acid. Think of it as a model for acid rain. And this is just distilled water with a pH indicator in it that makes it blue when it's neutral or basic, and it'll turn pink if it's at least a little bit acidic. Let's see how much acid it takes to turn our distilled water a little bit acidic. Let's do one drop. Oh, wow. It's already pink, guys. It's already pink. One drop. But let's try the same thing with the river water. Let's see how many drops it takes before it turns... I'm just dumping it in there. We getting it? It's starting to happen now? There. It's sort of half and half. Got a half and half transition. After like 5 or 6 or 7 drops, that was a lot more. And we're not even all the way there. Get a little bit more. A little bit more. A little bit more. Come on. There we go. There. Now it's acidic. Why does this happen? It's because this river is protected by limestone, which is calcium carbonate that is present throughout the entire river system. Acid rain dissolves the calcium carbonate in the limestone. That carbonate washes into the river and acts as a natural buffer. A buffer solution resists changes to its pH when a strong acid or base is added to it. So the Clark Fork's geochemistry explains why acid rain isn't as devastating here as it is in, say, the Adirondack Mountains of New York, where there is no limestone. Buffering is a big deal in chemistry. We buffer swimming pools to prevent the chemicals from damaging our skin, and we buffer soda pop to prevent the acidic flavorings from damaging our teeth and tissues. We even have buffers in our blood to keep our internal pH constant and ourselves healthy. I think it's important to learn about something that powerful. How about you? A buffer solution is a mixture of a weak acid plus its conjugate base, or a weak base plus its conjugate acid. These are called acid-base pairs. Weak, in reference to acids and bases, means that they only partially dissociate. It's actually their weakness that makes them great buffers. Since they don't fully dissociate in water, the undissociated buffer can act as either a source or a sink for protons, which helps neutralize a strong acid or base that's added to the solution. It's really all about equilibrium. For example, when a weak acid like acetic acid is added to water, a tiny fraction of it dissociates into its constituent ions, acetate and hydrogen ions, or protons. I was recently pouring a bunch of a solution like this all over my fish and chips. Vinegar is just a 5% solution of acetic acid. But the reaction is reversible as well, and that's where equilibrium comes in. Say we have a 1 molar solution of acetic acid. To make the solution a buffer, we need to increase the concentration of acetic acid's conjugate base, acetate, by adding sodium acetate to it. That would be a good way. Sodium acetate dissociates completely, thereby providing a ton of acetate ion. To see how this works in practice, let's add enough of that salt to make a 1 molar solution. We know how much acid and how much acetate we put in, but the important thing is the pH. And to determine that, we have to know how many protons there are. A rice table will help us keep track of everything. The reaction, R, we're interested in here, of course, is the dissociation of acetic acid. We can ignore the sodium from the sodium acetate, although it will stick around. It's just a spectator ion that won't take part in any reactions. Our solution contains initial concentrations I of 1 molar acid and 1 molar acetate. We haven't formed any hydrogen ions yet, so that stays at 0 for now. We don't know how much the concentrations will change, C, so we call it X. The acid loses X, and both ions gain X. So our concentration's at equilibrium, E, then our 1 minus X, 1 plus X, and simply X in that order. Now just put the numbers into the equilibrium formula, 1.76 times 10 to the negative 5th. But when chemists work with dissociation equations for acids and bases, they give the KEQ a special name, the acid or base dissociation constant. The symbol for this kind of equilibrium constant is Ka for an acid or Kb for a base. So use the equilibrium expression for acetic acid and put in the Ka and the equilibrium concentrations from the rice table. With a little simple algebra, it simplifies. That doesn't look simplified. I guess you could call that simplifying, but that's like quadratic. I don't want to do that. So here's a little trick to make this a lot easier. See, acetic acid is a really weak acid, so only a tiny fraction of it dissociates, which means that X is super small. If it's so small that after rounding for significant digits it doesn't change our answer at all, then why not just drop it? And that first X for the hydrogen ion has more effect because it's multiplied, but the other two, let's just forget they're there and see what happens. If we go back to where we plugged in all the numbers and simply drop the two x's that are being added and subtracted, the rest of the problem cancels out, leaving x to equal 1.76 times 10 to the negative fifth. The rest is a breeze. With a couple of taps of the calculator, we find that the pH is 4.754. But here's the big question. What if we try to push the pH out of whack? The whole point of a buffer is to resist that, right? If I had a strong acid, like, say, hydrochloric acid at a concentration of like 0.1 mole per liter to distilled water, the pH will change very quickly to like very fast dropping. Yes, now we're at like 3, pH of 3. Not a healthy environment for most organisms. So let's think about what would happen to the pH with a buffer in place. Even though HCl dissociates completely in water, releasing tons of hydrogen ions, when it's added to a solution that's buffered with acetate, the excess hydrogen ions join with the acetate ions to form acetic acid. Thus, that strong acid can't affect the pH much because the hydrogen ions are used up. To neutralize 0.01 molar HCl, or more specifically 0.01 molar H+, the acetate concentration must decrease by 0.01 moles per liter, simultaneously increasing the acetic acid concentration by 0.01 moles per liter. That leaves us with 0.99 molar acetate and 1.01 molar acetic acid. Well, pH is determined from the concentration of protons, which is in our equilibrium equation, so let's just solve for that. When you plug in the new acetic acid and acetate concentrations and the Ka, you get 1.80 times 10 to the negative 5 moles per liter for the proton concentration, which translates to a pH of 4.746. This is obviously not a big change from 4.754. In fact, I had to go out to the fourth digit to see the pH change, which isn't even justified if you watch Crash Course Chemistry on Significant Figures. But I have to confess, vinegar and hydrochloric acid, they may make things easier to understand, but they're not exactly super relevant in terms of practical chemistry. Instead, I want you to see how this works in the real world. So let's consider the buffering system of the Clark Fork River. There, the reaction between dissolved limestone and acid rain really happens in 3 steps. First, the solid calcium carbonate reacts with the protons from acidic rain to form calcium and bicarbonate ions. The bicarbonate ions each have 1 hydrogen. As long as protons are available, the bicarbonate ions can grab a second proton to become uncharged carbonic acid. As you can see, this chain reaction uses up 2 protons per molecule of calcium carbonate. That makes this process doubly powerful, and that explains why the Clark Fork River is so resistant to acidification. But, of course, buffers are not invincible. Add enough acid or base and even the best buffered solution will get overwhelmed. We call that threshold the buffering capacity of the solution, and we determine it in the lab using pH indicators through a process called titration. Earlier, I used a pH indicator that showed an acidic pH by turning pink, but there are lots of other indicators, each with different colors and a different pH where it changes. This is called the indicator's endpoint. Here we have 100 milliliters of water from the river, to which I've added some pH indicator. It's actually a mix of 2 different pH indicators, bromocresol green and methyl